the perspective, some of his perspectives from his very productive career looking at Biofloc technologies. Dr. Samocha, thank you for being here.
Thank you very much. Wanted to thank Dr. Andrew Ray and the other sponsors of this workshop for inviting me to give this presentation. Before I start, I wanted just to mention to you that basically what I'm trying to cover in 30 minutes time. Okay, I was trying to use this one.
Oh, yeah, sorry.
Okay, what I'm trying to cover in 30-minute time basically is covered with this book that originally been published by WAS because of some issue related to a word like mixotrophic that you will hear me using. Basically, WAS was not willing to continue to sell the book. Right now, we are in the process of having Elsevier publishing the book. The book comes with a tail that basically provide also video and Excel file that will help you manage the system. And I'll try very briefly to cover some of this topic. As we heard here, you can grow shrimp in clear water, Biofloc, and other. My preference here is to explain you how we were doing it in a Biofloc-dominated system, mixotrophic system, and I'll explain again what's the advantages of working with this type of system. Basically, previous reports showed that the feasibility of growing shrimp in Biofloc system. Biofloc is assemblage of living bacteria, algae, cyanobacteria, fungi, protozoan, and non-living component. Basically, when you are growing shrimp, there are different issues that you need to address, and here I'm trying to cover some, not all of them. Seed stock, water source, and salinity, dissolved oxygen and water mixing, especially important in Biofloc system. Water temperature, nitrogen species, including ammonia, nitrate, and the accumulation and solving the issue of accumulation of nitrate, pH, alkalinity, particulate matter, growth monitoring, which is also very important and a tool that we are using in our system, feed and feed management, and Dr. Browdy will talk about it also. Thank you. Waste disposal, which is also an important component, alarm system and power backup, natural light and microalgae contribution, biosecurity, probiotic, and diseases. Moving along, seed stock, quality. Eduardo Figueras talked about it yesterday, and certainly looking into the quality and evaluation of the seed stock and the different criteria are important. In the book, again, we have different criteria, how you can evaluate it. Good Hatchery will provide you also sheets with the quality of the post-larvae. Size variation, I'll talk about it a little bit later, and how you may want to address it. Transportation option, generally for the small producer, you will get it in styrofoam boxes packed, and then you need to do the acclimation. Proper acclimation is also important. Bear in mind that generally you get the shrimp in low pH and do not increase the pH very quickly. Take care of it. The issue of the quality, SPF, we stressed it yesterday, the issue of fast growth line and tower resistant and other line that might be available. And PL size, as I mentioned earlier, that you need to be aware and manage your system accordingly. Water source and salinity, depending where you get the water, then you may or may not need filtration, disinfection, probiotic, and other. Probiotic, I should stress that we strongly recommend using it, as Doug mentioned earlier, that you can get the benefit from it. Now, if you are working with natural seawater or artificial seawater, with artificial seawater, you need to be aware of the sources of the salt. Some of the salt will be toxic to the shrimp, so be aware. And make sure that you are not going to kill your shrimp without testing it at the beginning. The salinity impact on low salinity, we'll talk about it later, but you need to be aware of. Bringing oxygen into the water, there are different ways you can do it. Air blower with an air diffuser, airlift pumps, different management of inducing the oxygen into the water, there are some limitations in terms of the biomass capacity and carrying capacity of this method. Other methods are the Venturi type, whether it is a true Venturi or the A3 injector. And again, the carrying capacity will vary, and we have found after our work with the A3 injector that we were able to maintain more than 9 kilo of shrimp biomass per cubic meter in no water exchange, Biofloc dominated, with only using the ambient air. So that's very, very significant, and we have not used liquid oxygen or any oxygen. Other method of fountain type, again, you can use it, and there are some issues that you need to address related to it. In any operation, again, it will be good to have oxygen sources that you may be able to use if you need it because of different things that may happen, including algal crash or biofloc crash, overfeeding and other, so having it handy will be very useful. Our oxygen monitoring system, we found it very, very useful, and I'll show you some example how it helped us manage the system much more efficiently and improve the production accordingly. So the system can be programmed to let you know there is a problem or even take few action to improve the situation until someone comes and take care of the problem. Water temperature is important in order to get the best performance of the shrimp. It doesn't mean that you cannot grow them at 20 or below 20, but growth rate will be low, and basically the bottom line, you need to make money, and optimal temperature will help you get there. Optimal range, as we heard earlier, you may want to be in a 28 to 32. Below that, shrimp will grow, as I said, but think about how much it will cost you to reduce growth. Tank design in terms of insulation and then structural insulation is very important. Here we see also passive control if you're using greenhouses, and there are different type of greenhouses that can be used, including 2-layer with insulation material that will give you some diffuse light that I really like, that will help you conserve energy significantly. Other option that you may want to consider, again, depending on the system that you are using, you can get an increase in temperature either by in a passive situation where you are using, for example, injector. If you are to use air that is hot, if you bring it from outside or inside the greenhouse, it can help you maintain or bring the temperature 2 to 3 Celsius degree accordingly without investing more money. Active control, again, mentioned earlier, different types, heat exchangers, heat exchanger, space and submergible heater. All of this can be done, and you need to think about how to maintain the heater so it will stay still very effective. In terms of the ammonia nitrogen species, you need to be aware of low salinity on the nitrogen impact on the toxicity. The lower the salinity, the more the toxic the impact. It is common to express the inorganic nitrogen compound by their nitrogen content, namely NH4N, ionized ammonia, and unionized ammonia, NH3N. The sum of the two, which is oftentimes called ammonia nitrogen or simply ammonia, NO2N and also NO3N. And you need to be aware, based on the test kit or the method that you are using, whether or not you are monitoring NO2 or NO2N or NO3, NO3N, it makes a big difference. Ammonia is a soluble end product of protein catabolism that excreted in their unionized form, which is toxic to the shrimp. Thus, you need to be aware of the issue of the impact of salinity, temperature, and basically you see here an example of 30 parts per thousand, 7 pH, and temperature of 28. You'll have only 1% of the total ammonia nitrogen in the toxic form. On the other hand, if the temperature, if the pH will increase to 10, then you are dealing with a much, much higher percentage in the toxic form. It can be removed by algal, micro, or macro photosynthesis, oxidation to nitrite, and nitrate by autotrophic bacteria, and direct conversion to microbial biomass. Here you see the conversion of the ammonia by heterotrophic bacteria. Basically, they take the ammonia with the organic carbon source and some alkalinity and oxygen and convert it to bacteria, water, and CO2. The increase in microbial biomass production is 40 times greater, and consumption of oxygen and CO2 production are higher than in nitrification. That's the reason why, I explained later, we are using the mixotrophic system. If kept as fully heterotrophic, large effort and resources are needed to maintain these systems. To operate properly, the system requires constant energy supply to maintain it. And carbon supplementation is a must. Moving along, as demonstrated, heterotrophic bacteria incorporate ammonia N directly into microbial biomass, no generation of NO2 or NO3. When using 35% crude protein feed, only 1/3 of the dissolved organic carbon required by the heterotrophic bacteria is available from the feed. To assimilate all of the available ammonia and supplementation of dissolved organic is needed. We are using the 1 gram of total ammonia nitrogen, 6 gram of organic carbon in order to deal with the ammonia. Use of organic carbon when you are using it, here is an example. Basically, heterotrophic conversion in a tank of 40 cubic meter. If you have 4 milligram per liter, you can see here if you are using molasses of 4% carbon, you calculate and you get to basically 3.08 liter of molasses, or 3.8 multiplied by 3, and you get 4 kilo of the molasses. You can also calculate it in white sugar. Moving along, to prevent high level of ammonia in a culture tank when nitrifying bacteria were not established, you can use the organic carbon. To avoid algal-dominated water in culture tank, again, you can use it in case you had removed too much of the bacteria. And gradual application of the organic carbon is a must, otherwise you'll have an decrease in dissolved oxygen, and operator must have the capacity to maintain dissolved oxygen in case of something like that. Autotrophic nitrification, basically you have the ammonia, you have oxygen, you have alkalinity, inorganic carbon supplementation, you get bacterial biomass, you get NO3 as an end product, water, and some CO2. Requires supply of ammonia, oxygen, inorganic carbon in the form of alkalinity and adjustment of pH. Targeting a mixotrophic system where 1/3 of the bacteria are heterotrophic and the rest are nitrifying bacteria. When mixotrophic system is reached, basically this system is very, very stable. We have demonstrated that basically we can get very high biomass under this condition. You can enhance the nitrification by using bacterial supplement, and basically Fritz-Zyme or other are available on the market, and you can use them to expedite the establishment of nitrification or nitrifying bacteria. Here I just wanted to show you basically that we were able to maintain and get over 9 kilo an average here with FCR of 1.4, 1.5, growth per week 2.1. This is 500 animals per cubic meter, juvenile, and look at the ammonia that was about 2 here, and then drop and stayed stable. The same is true for nitrite, very low, and nitrate was keep on increasing. So basically, we were able to do that without adding any drop of organic carbon, only taking care of the alkalinity and pH, and of course, maintaining optimal concentration of total suspended solid. Nitrogen species toxicity. Salinity impact, increased toxicity of ammonia, nitrite, and nitrate with a decrease in salinity. Nitrite toxicity can be avoided either by maintaining a heterotrophic or mixotrophic system. No nitrate issue is in heterotrophic system, as explained. Nitrate buildup in mixotrophic system require removal, as we'll describe later. Denitrification is a 4-step anaerobic microbial process that chemically reduces NO3 to nitrogen gas. NO3 is reduced to NO2, which then is reduced to N2O with the final step of reduction of nitrogen gas. To avoid H2S production, it requires adequate sources of organic carbon, redox potential, dissolved oxygen at certain level, nitrogen supply, nitrate supply, and temperature. In a perfectly balanced system, and that's very important, you can bring back the alkalinity that you were adding on a daily basis because it will be generated and brought back into the system. Other method that can be considered in some situation, anomorphs and photosynthesis. Moving along into pH alkalinity and particulate matter control in this Biofloc system. pH level decrease over time if you don't maintain it. Require adjustment to maintain optimal for microbial activity. Alkalinity consumed mainly by nitrifying bacteria, use of 7.14 milligram calcium carbonate for every 1 milligram of total ammonia nitrogen oxidized to nitrogen N. Require adjustment to maintain optimal nitrification activity. There are different chemicals that you can consider for adjusting alkalinity, including the bicarbonate, carbonate, and other. And you need to consider availability as well as the impact on the water. Make sure that when you're adding it, you do not change the parameter very, very drastically in a short period of time. Particulate matter control. Biofloc systems are characterized by continuous generation of biofloc of organic matter for the most part, and you need to maintain it. If you don't maintain it at optimal level, this may result in affecting the system performance, including affecting the shrimp performance. Monitoring and control of particulate organic matter are essential to maintain the optimal condition. Then monitoring method, you can use the Imhoff cone. Most of the people will prefer to use it because it's easy. You look at the settleable solid, you measure it in milliliter per liter. We didn't find it as a very useful tool. We prefer to use the total suspended solid. Basically, you take a sample of water, filter it, put it in the oven, dry it, and then you can calculate what is the milligram per liter of particulate matter you have in your system, and then you can control it to the level that you want. The level you want to maintain is between the 250 and 350. Later on, I'll explain why we would like to be in this range. There are different ways that you can control the particulate matter. We like to go with as simple system as possible. You can use the drum filter, you can use other means to deal with it, and also moving into the settling tank. In our setup that we advocate, basically, we have one pump that does all of the job for us, including oxygenation, mixing, firing the foam fractionator, as well as providing the water to the settling tank. Waste disposal. What we would like to do is to collect, basically, when you work with the foam fractionator or with the settling tank, you collect a lot of waste that has a lot of water content, so we try to dewater it, and then you have the concentrated matter that you can use either as a fertilizer or other uses that can be considered. Growth monitoring and feed management. Growth monitoring provide information regarding the shrimp performance. You need to collect representative sample, use suitable net, that's very important. If you have a high size variability or other, using inadequate netting will not give you a representative sample. Also, you need to think about individual versus the group weight in order to know where you stand, especially when you are dealing with a post-larvae with a high size variability. You need to accommodate all of these shrimp, small one with an adequate particle size. Use of observed growth rate, survival, and assume FCR to calculate daily ration size. For example, if we assume that we have 50,000 animals stocked in the tank, survival, and we assume that we have certain mortality, and at the time that we are sampling, we assume that we have 90% survival. We assume certain FCR, and again, that's based on experience and observation, and assumes a certain growth. Then you can calculate in this regard, the amount of daily ration will be 15.3 grams. So that's what you are going to put if these assumptions are correct. And you need to observe the system and make sure that even this quantity is not too much. So feed and different factors that you need to consider. Palatability is very important. Better shrimp growth in biofloc than in clear water. It's been proven time and again. Feed quality, impact, and high density culture require good quality feed. Here you can see a study that we have done with the same level of 35% good protein feed, 67 days of grow out. Here is another high density, 35 good protein, and what we found here, basically the size of the shrimp is larger, growth was over 2 grams a week, biomass higher, yield 9.7 as compared to 8.7, foam fractionator and settling tank, namely how much effort you need to put into the water in order to maintain the optimal condition for the shrimp to grow. You see also differences in the number of hours of operation, foam fractionator, settling tank as compared to this. Now, bear in mind that there is a cost associated with it, and what you need to make sure that the cost can justify, or the performance can justify the investment in the cost, extra cost of the feed. Feed management, particle size is very important, especially if you are dealing with a very young post-larvae with a high size variability. It's been demonstrated time and again that if you are feeding small shrimp too large particles, it can result in stress of the animals. You can look at the hepatopancreas and determine it. We like to use intermittent FCR, basically amount of feed that we fed from the last feeding, as well as the amount of feed we fed from the beginning until the day we sample, and then we can calculate based on assumed survival and biomass where we stand. And if we find that intermittent FCR is 2, for example, it means that we wasted a lot of feed, and the implication on water quality can be also very important. Now, distribution by automatic feeder, we found that it is very, very useful and small quantity at a time, and here's why. And when we started to work in this system, we used to feed 4 times a day, no monitoring of the oxygen very regularly, and what we have found that after feeding, oxygen drop, recovery, and at night we were not feeding, then oxygen increase, and then all along you see the trend of drop in dissolved oxygen. By feeding continuously, we avoided it, and we have started to get much better shrimp performance in this particular case. Alarm system and power backup. Safety system, again, issue regarding to theft, predator control with the standard security measures to prevent entry of unauthorized personnel and predator, defensive response, perimeter fencing, motion sensor, security, lighting, camera, worker living on site, culture tank in lockable building, electrified wire around the perimeter, and predator traps depending on the location. Alarm system, you can have these alarm systems that will alert you of low DO, power outage, low high water level, temperature, oxygen flow, high water level sensor. All of these are available, and again, if you have it in place, it will reduce the chance of losing a crop, because when you're dealing with high biomass, you can lose a crop very quickly. Natural light versus artificial light. We have found that basically when we are exposing the shrimp into natural light, we had also production of microalgae in a small quantity, and especially when we have diatom growing in the water, we had a better performance of the shrimp under this condition. We monitor the concentration of the diatom in the water, and thus we were able to come up with this conclusion. Biosecurity, probiotic, and diseases. Biosecurity issue related to it, purchase of post-larvae from commercial hatchery which provide health certificate, limit access of a visitor to the culture tank, use foot bath and hand sanitizer, minimize moving equipment and tools between culture tank, prevent access to disease carriers such as crustacean, insect, and bird. And then probiotic, as you mentioned, as Doug mentioned also, we like to use a probiotic, but when we use probiotic, you need to know what's going on. You do not just dump the probiotic and walk away. Thus, if you can monitor and see the impact of the probiotic on the water, so you can increase dosage or bring another probiotic if needed, and this can help you. Here, for example, we use a TCBS, and we kept the green forming colony very, very low. The yellow forming were in a much higher concentration, and this resulted in extremely very good condition, as you will see later. Regarding to disease, use of PL from a hatchery that provide health certificate with a reliable testing method. That's very, very important, as mentioned yesterday. Request the hatchery to provide PL scoring sheets together with a health certificate. Avoid shrimp exposure to suboptimal water quality conditions such as low DO, high-low temperature, low-high pH, high TSS, settleable solid, ammonia, nitrate, and other. Now, I want to, let me go back here. I wanted to mention also that under optimal condition, you can expect the shrimp to grow at a very fast growth. I mentioned earlier 2 grams a week, but you should be able to get 3 to 4 grams a week if you provide the shrimp optimal condition. Moving along, very briefly about the book that I mentioned earlier. This is design and operation of super intensive Biofloc dominated system for the production of the Pacific white shrimp. And basically we try to put together our experience, our knowledge in this book and provide suggestion how to go about raising shrimp and avoid losing your money because of malinformed information. Objective of the manual is to encourage expansion of sustainable Biofloc dominated as developed in the our system, our lab. Funding was provided by NOAA through a National Sea Grant. Participants were Texas A&M AgriLife Research, Auburn University, Florida Organic Aquaculture, and Texas Sea Grant Extension Service. The manual described design and operation of probiotic system developed over 20 years of experience at A&M, emphasizes the most recent L-Vaname production in our system, and it was written in non-academic style to target wider group of stakeholders, especially entrepreneurs interested in building a pilot Biofloc dominated system. It has 15 chapters plus Excel sheets and short video. Chapter 3 is a Biofloc, its composition, structure, development, and advantages. Chapter 5 deals with site selection, production system. Chapter 6, system, treatment, and preparation. 7 deals with water quality management, controlling DO, ammonia, pH, alkalinity, temperature, salinity, suspended solid, turbidity, and other, and waste product. Chapter 8 deals with the next nursery production. 9, grow out, disease and biosecurity, economic, special chapter on economic based on our result as well as forecast of full-scale setting and running the what if sensitivity analysis, and you will see much better number than what we have heard yesterday that can encourage you in this regard. And then chapter 15 is a troubleshooting table that basically tells you what if and how to go about it. I should mention that this book was published originally as an e-version. E-version has a lot of hyperlinks that you can click on and go into different places, picture, table, and other. And the book, it does not have the hyperlinks, but it has the memory stick I mentioned earlier that basically enable you to see some of the information. Do I have enough time to continue or not? 3 minutes, okay. So nursery production of Pacific white shrimp in a 100 cubic meter raceway. Basically, we took the post larvae and stuck them directly into the tank. This is the tank, the way you look at it, 100 cubic meter, a different component. We won't go through it, but basically it's been operated with the injector, A3 injector. And basically, here you look at how it looks in real life. Again, these are the snorkel that takes the air and mix it with the water. You can take the air from the top, you can take the air from outside the greenhouse. That's the passive control of the temperature that I mentioned earlier. Some of the setup of the raceway. Here we use animals of below 1 milligram in size, very high size variability, about 60%, continuous feeding, and then different parameters that we monitored. We stocked them at the raceway at 540 post-larvae per cubic meter. We like to work with density per cubic meter and not per square meter, as the shrimp spend their time in the water column. We use nitifier, we use probiotic, and all of the listing of it, I won't go through it, the foam fractionator, the settling tank, the concentration of the waste, and some of the water temperature. At the beginning, we were working with a very low temperature. We didn't have temperature control, so we had 22 Celsius degrees. So that's the reason why this was 62-day nursery trial. Otherwise, it would have been much shorter. Here you see the ammonia nitrite and other indicator, basically, that stayed very low, and total suspended solid, soluble solid. And here again, we monitor the bacteria, but TCBS, the green and yellow forming bacteria, and as you can see, very low level of green forming bacteria, Vibrio, and the yellow. And what you want to see here, and that's what's significant, is the fact that we were able to maintain, to get to almost 6.5 gram animals, minimum and maximum size. The coefficient of variation been reduced from about 60% to 31, 35%, 94, 97% survival, FCR of 0.8. So all of this basically in biomass load of 3.4, 3.2 kilo per cubic meter. We use only one pump of 2 horsepower, and we were very, very happy. And basically what this tells you, that if we can get to the 0.8 FCR with a 6.5 gram, we have a good possibility to, with adequate feed management, water quality, and other, with the seed, to get to below 1 FCR in our super intensive system. And I believe right now we should stop here. Thank you very much.